So we just want to continue on this work and energy. Last time we showed how we could calculate the work, and if we looked at the entire system, we didn't have to worry about tensions, we don't have to worry about normals either. So, but when we did calculate the total work, we want to know, what does that equal right here? Well, suppose we go back to Newton's second law, sum of the forces equals ma. Suppose we dotted both sides with S right here. Well, this side is just the sum of the works right here, since work is defined as F dot S right here. And now over here, you remember for A, we had two different types of A. We had an A due to going in a circle due to your change in direction, which is V squared over R. And we had the other A due to your change in speed, which is just your dv dt, but we'll just keep it as A right here. It's the one we used for our constant acceleration equations right there. Well, when you distribute this through, this is perpendicular. Inward is perpendicular to the way you're going right here. So I can get rid of this term. Anytime you're going in a circle, any inward force doesn't do any work because it's perpendicular to the way you're going. So the only term we have is this one dotted with that. And these two are parallel, so the cosine of the angle between them, the cosine is 0, so it's just m times a times s right here. There's the total work right there. Well, if we go back to our constant acceleration equation, v squared equals v naught squared plus 2a x minus x sub naught, where x, the distance you move, is s, you notice I have an a times an s right there. If I solve for that a times s, I'll just divide out the 2. It's just v squared over 2 minus v naught squared over 2. And so that way, the total work, the sum of all the works right here, is just m times as. So it's just m times this, which is 1/2 mv squared minus 1/2 mv naught squared. This is a difference, since this is units of energy, we call this the change in kinetic. Kinetic just means moving energy, where kinetic is defined as 1/2 mv squared right here. So it looks like our main equation then is, if we calculate the total work, all the changes, remember works were transfers of energy, it should just go into changing the kinetic energy of the object right there. So that's really the main equation, but we want to put it in terms of parameters we're used to right here. So let's just suppose that we have some system that has gravity in it, and it's got normals, and it's got tensions, and it's got frictions, and even your hand force. It's got everything in it. It could have multiple ones in there. And so the sum of all the works right here should equal that change in kinetic energy. Well, we know that term is always 0 because this is always perpendicular, and we know that's 0 because we're looking at the entire system. So we just got these three terms right here. Now, let's just look at what is the work due to gravity. Let's just dwell on that for a minute right here. Suppose we have an object that has some mass m, and we're going to move it from here to there. From here to here. It's going to go over a distance d, and it's going to go up. Well, that was at h1, and we're going to take it up to h2. We're going to move it from here to here. And I just want to know how much work does that take to go move an object from here to here. And so, well, let's just take this path. Let's just come across and then go straight up. Well, and I just want to find the work due to gravity, not the work I have to do on my hand to move it. I have to use my hand to move it. I just want to know how much gravity does. Well, if we go from here to here, mg is down, s is this way. That's perpendicular. So at least from A to B, there's no work because you're perpendicular. Now, when we go up this way right here, the work from B to C, S is opposite mg, so the angle between them is 180, so you get a minus. So it's mg times that distance, and that distance is just h2 minus h1 right here. And then we'll just throw the mg inside. So there is the amount of work it took to go from here to here. So the total work from A all the way to B going this path, well, that was 0 and that was this, so it would just be this right here. Well, let's pick a different path. Let's say we want to take this path too. We just want to go straight diagonally up there. Well, again, now the work due to gravity is mg dot s. mg is straight down, s is up that way, right there. Well, if this angle is theta, or that angle is theta, the angle between mg and s is 90 plus theta. So it would be mgd cosine 90 plus theta. Well, the cosine of 90 plus theta is minus sine theta. So this just becomes mg minus mg d sine theta. But now, if we think about this, if that's d and that's theta, then d sine theta is just the opposite side of d right there. Which is h2 minus h1. So it just becomes, so d sine theta is just h2 minus h1. Or if I distribute that through, we get the work due to gravity is minus mg h2 minus mg h1, which is exactly what I had before. So the work it takes to go this way is exactly the same amount that, which is the same there, which is the same if I come over here, took a few loops, came all the way around to here, or if I took it around the moon, around Jupiter, and brought it all the way back to here, the work would be exactly the same. So I don't care what happens between here and here. All I have to do is take a snapshot of it there and a snapshot of it there, and I know the work, which makes life a lot easier. I don't care what happens in between right here. Now that doesn't happen for all forces. It only happens for certain ones. And for these ones that it does work, we call these conservative forces. Now I should tell you that in this sense, remember everything is backwards. Work really makes life easier. Conservative is actually a good word in physics right here. So it's exactly the opposite like in politics or something right here. Okay, so here it means a good thing right here. So it only depends on the endpoints. It doesn't matter how you got there right here. And since it only depends on the endpoints, we could call this minus a change in a potential energy. Remember, we said mgh was potential energy, where U due to gravity, that's our potential energy, is mgh. Now, it doesn't matter where you call h equals 0. You notice I called the ground way down here, but you could have called it here, I could have called it there, I could have called anywhere I want. The only thing I have to do is I have to call up positive. Why? Because we already assumed it when we did the dot product and everything. So we have to call up positive right there. And so now, you'll notice as you keep taking more and more physics, you're going to find that there's a lot of other forces that are conservative besides gravity. And again, when you have a conservative force, you can always write the work due to that conservative force as a minus a change in potential energy. Again, we'll see more in this class. You'll see them in 4B and so on right here. So, okay, and so now we can replace this term right here with what? Minus a change in a potential energy due to gravity, where the potential energy due to gravity was mgh. Okay, so we're going to try to work this problem down to where we got something that's very simple. Okay, we'll pick that up on the next one.